First, we will discuss the amplitude. The value of a in our sine function represents the maximum distance of the curve from the center line. This is also called the amplitude of the function. It can be observed in this graph that the amplitude is from 0 to 1, therefore the amplitude is 1, and the a value in our original function would be 1 times sine of x, which is often just written as sine x. Therefore, the amplitude of the standard sine curve is 1, and the amplitude is also half the peak-to-peak value of the waveform. So if we have our maximum peak here, our upper peak, and the minimum, the distance from the lower peak to the upper peak is 2, and therefore half of 2 is 1, and that is the amplitude of our waveform. When we state the amplitude, we always give the positive value. Therefore, the amplitude is represented by the absolute value of a. Remember, whatever a is, what the absolute value function will do is make that value positive. For example, with the sine curve, y is equal to negative 2 sine x, our amplitude is positive 2. Note, because the absolute value of a negative value is positive. When we have a negative value for a, what it does is flips the graph vertically. For example, if y is equal to negative sine x, that means that our amplitude is just positive 1, so it's the absolute value of negative 1. Okay, say we want to graph y is equal to negative sine x. First, consider our function y is equal to sine x, so our sort of home curve. We can graph negative sine x by just reflecting it in this case, the x-axis. So it's a vertical reflection of our original function. Whereas with sine x, our function initially increases, goes to 0, decreases, and increases back up to 6.28. Y is equal to negative sine x, initially decreases. So compare the two curves below. We want to identify what the amplitude is of each of these curves and compare their graphs. The top graph is of y is equal to 4 sine x, whereas the bottom graph is equal to negative 4 times sine x. So the only difference between these two equations is the a value. The top one has an a value of 4 and the bottom one has an a value of negative 4. But when we take the absolute value of each of these a values, you end up getting an amplitude of 4 for both of them. And you can see by observing each of these functions, both of them have a period of 2 pi. They have zeros at pi, and as well as 0, and they are vertical reflections of one another. And it can also be observed that our amplitude is 4. In each of the graphs. So the distance from the x-axis to the peak is 4 units. For question 2, we want to list the amplitude and peak-to-peak value for each of the given equations. Given y is equal to 6 cos x, we find that the amplitude is 6 and the peak-to-peak value is 12. And completing the rest of the chart, so pause your video and compare your results to what's calculated here. Now we will define and calculate the period of various trig functions. The period of a waveform is the length of one full cycle of that curve. This is the horizontal or x distance between any point and the next point at which the same pattern of y values starts repeating. For y is equal to a times sine bx, or y is equal to a cos bx, we can define the period as being equal to 2 pi divided by b. In the last video, we looked at how the period of sine x and cos x were both 2 pi, and in those special cases, b is equal to 1. And when b is equal to 1, the period is equal to 2 pi, as shown in the first video. Recall in the first video when we looked at horizontal compressions, where we had that g of x was equal to f of b times x, where we had a horizontal compression. In Module 1, we talked about if the absolute value of b is greater than 1, this results in a horizontal compression, which in turn reduces the period, whereas if the absolute value of b is less than 1, this results in a horizontal stretch, and it increases the period. The frequency of a waveform is defined as the number of cycles that are completed in one single unit of the horizontal axis, so often denoted as x. Written as an equation, frequency is equal to 1 divided by the period, which is equivalent to b divided by 2 pi. And that is when we're measuring the frequency as the number of cycles per radian. The equation above for the period is also given in radians, and both of these measures can be converted to a measure out of degrees by performing the appropriate calculation where pi is equal to 180 degrees. In the graph below, we're going to compare the curves for f of x is equal to sine x, our original function for sine x, and g of x is equal to 3 times sine x, as well as h of x is equal to negative 4 times sine x. We can see that the amplitude of each of these functions is very different. So one has an amplitude of 1. The blue curve, g of x, has an amplitude of 3, and h of x has an amplitude of 4. But what does remain the same is the period, and the period is identical for each of these graphs. And if you recall, we calculate the period as being the distance along the x-axis to complete one full cycle of the periodic function, and in this case, one full cycle for all three of the curves is completed in 2 pi. All three of these curves repeat every 2 pi radians, and the natural period for the sine wave is 2 pi. Practice. So pause the video, give this question a try, and then play the video and compare your solutions to what's worked out here. Example 1. Y is equal to 2 times sine of 3x. A graph of the function is given below, and we are asked to visually estimate the period of the curve. If we estimate, we can see that this periodic function completes one full cycle up until just after x is equal to 2. We need to estimate this point, and we can estimate where 2.5 lies. And then if we subdivide it, we could approximate that it occurs at approximately, say, 2.1 units along the x-axis. Using the formula, we can estimate the actual period of the trig function. Remember, the period is equal to 2 pi over b. In this case, our b value is equal to 3, and this is equal to approximately 2.0944. In example 2, we have that y is equal to negative 3 times cos of 4x. Again, we're given a graph of this function, and we can estimate the period of the curve. I tend to either go from valley to valley or 0 to another 0 to count a full period of our trig functions. So here we want to figure out where one entire cycle occurs, and it really doesn't matter which cycle you use because they're all even and equal. So you could estimate that one full cycle occurs sort of halfway between 1 and 2 at 1.5. Whereas this value can also be calculated by using the formula 2 pi over b. Remember, our b value is equal to 4 for this example, and we find that the period is equal to 1.5708. Next, we will look at sketching waveforms without a table of values based on the information we have from its amplitude and period.